So today I'm going to tell you about something called the freshman's dream. So this is a very common mistake that you might be tempted to make in algebra. If you're naively playing around with exponents, a plus b squared is a squared plus b squared.
Why is this called the freshman's dream?
I tried to look this up a little bit. It's less than 100 years old. There are some text references to saying that this is a fallacy you might expect or you might teach incorrectly to freshmen, but it's gained sort of a name of its own, and it's referred to it like that. It even has its own Wikipedia page at this point.
You are like a university professor type person, aren't you? So you deal with freshmen quite a lot. Would a freshman actually make that mistake of thinking that's true?
Well, it happens on a regular basis, right? So, and maybe it happens a lot earlier in school as well. There are variants of it that people also make all the time and just playing around with other things. Let me put a random, another way to write it down. You might be tempted to hope that the square root of a sum is the sum of the square roots. And of course, both of these things are false. This is very easy to see. Just for some silly example, of course, 1 plus 1 squared is 4, right? Which is not the same as 2. 1 squared plus 1 squared.
What is the correct way to do a squared plus b squared?
Great. Back when I was in school, we called this FOIL, but you want to expand this out term by term, right? And so here, the freshman's dream forgets all of the mixed terms, or the middle terms, so the 2ab. So while it's false in general, right, it's true if 2 happens to be 0. Today I want to talk to you about the scenarios in which it is true, right? And some ways where you can exploit it, and some things where you can see that it's true and why it's true.
How are we going to do it? Where do we start this journey?
All right, so the start of the journey is really to talk about clock arithmetic. In clock arithmetic, you treat all numbers the same if they differ by 12, the number of hours on the clock. In usual clock arithmetic, two numbers are the same if they differ by even a multiple of 12. So 1 o'clock, 13 o'clock are the same, 12 o'clock, 24 o'clock, 36 o'clock are all the same. We just want to treat all of the whole numbers the same if they differ by multiples of 12. So if you fast forward 50 hours, you have increased whatever you had by only 2 instead of 50. For the freshman's dream, I want to kind of play on that and talk about the 2 clock. Imagine a clock where instead of having numbers from 1 up to 12, it only has, say, 1 and 2. Right? There's only 2 hours that are accounted for. That leads you to the idea, well, what if I just play around with numbers and I treat all of them the same if they differ by 2, right? So 1 o'clock, 3 o'clock, 5 o'clock are all the same, 2 o'clock, 4 o'clock, 6 o'clock are all the same, and playing off the same idea, I could go in the other direction too. Minus 1 o'clock is the same as 1 o'clock, minus 5 o'clock is the same as 7 o'clock. So I treat all numbers the same. In particular, 2 and 0 are the same in 2 clock arithmetic, or mod 2 as you would call it. There's only really 2 numbers up to this equivalence that you'd play around with, right? There are the odd numbers and the even numbers, right? So either you're an odd hour or an even hour, and there's nothing else on this clock. So the freshman's dream, when you're playing around with 2 clock arithmetic or mod 2 arithmetic, is going to be true, right? So if 2 and 0 are the same thing, of course, this middle term just goes away completely, and I end up precisely with the freshman's dream. A plus b squared is equal to a squared plus b squared.
Because that 2 no longer has any influence.
Right. This 2 here is the same thing as 0, so no matter what I put in, it doesn't matter. When I'm playing around with arithmetic on the 2 clock, I might write 5 plus 4 squared. Now, I could add these 2 together and get 9 squared, so it gives me 81, which I know is the same thing as just 1 on the 2 clock. All right? And of course, that's the same as if I did 5 squared plus 4 squared here. Again, this is really 1 o'clock plus 0 o'clock, or 1 o'clock plus 2 o'clock, however you want to say it. Right? Gives me 1 o'clock, and so the equations all still hold, right? And it's because whatever I had from these middle terms didn't matter, right? So it was 0 mod 2.
Okay. If we lived in a world where the number system was mod 2, the freshmen wouldn't be mucking up. They'd be quite correct in how they expanded that equation.
It's almost like you're saying that the world has only daytime and nighttime, and all that matters is whether the sun is out or whether it's not. Everyone, at some point, a lot of people make the mistake of trying to write down square root of 5 plus the square root of 4 equals the square root of 9 and hope that this all works. Again, if you're working mod 2 or on the 2 clock, right, then this just works, right? Square root of 3 plus square root of 7, of course, it doesn't equal this normally, right? But on the 2 clock, the square root of 3 again, well, 3 is just 1, right? So 1 squared is 1, so this might as well be 1 again. And of course, 1 plus 1 is 0. On the other hand, again, 10 is 0 on the 2 clock. Somewhat of a variant of the freshman's dream is that the sum of square roots is the square root of the sum, and that just works.
Cool. What happens to the freshman's dream in other mods?
You could talk about other clocks. So, for instance, I could talk about the 3 clock, right? And while in that case, I wouldn't want to play around with square roots. I would want to play with or squares. I would use cubes instead, right? So on the 3 clock.
So we're dealing with a different freshman's dream here, though, the a plus b cubed.
That's right. On the 3 clock, the only ones that show up on the clock are 1, 2, and 3, or 0, 1, or 2, depending on what your conventions are. On the 3 clock, now I get 3 equals 0, so again, we can convince ourselves that on the 3 clock, a plus b cubed is a cubed plus b cubed. Of course, again, normally never true. If I take a equals 1, b equals 1, I get 2 cubed, which is 8. And that's totally different than 1 cubed plus 1 cubed, which is 2.
Just to remind me, how would one normally expand this?
I really can break this up, multiply out 1 by 1. Take the first part, take a plus b squared, and then I have to multiply one more time times a plus b. If I multiply all that out and group all the terms, right, I'll get a cubed plus 3a squared b plus 3ab squared plus b cubed. And again, because we're working on the 3 clock, in much the same way, I have these 3's showing up here, right? And both of those don't matter, right? So the 3 times anything, right? Any multiple of 3 is 0 on the 3 clock. So again, this works. And I can do the same games with cube roots and things like that in this case as well. So I guess the next thing I want to tell you about is why this works, or what might be true more generally, right? More than just on the 2 clock and the 3 clock. And so that leads us very naturally to the binomial expansion and to Pascal's triangle and things like that. If I want to do this on other clocks, bigger clocks, the first thing I need to know for sure is how to take that expression a plus b to the something and write it all out, right? So here we did it for 3 by first expanding the square and then multiplying again, and I had to group all the terms. The first thing to say is there's a shortcut. I can just tell you what it is without having to expand it all out. So this is the binomial expansion. But here I have Pascal's triangle. Here I'm going to start off with a 1 in the first row, right? And in my mind, it's blanketed by zeros across it on both sides. And as I descend, I just add 2 numbers above each other to create a new row, right? So 0 and 1 gives me a 1. 0 and 1 gives me a 1 over here, right? Now at this point, 0 and 1 gives me a 1 in the outside, but 1 plus 1 is 2. 0 and 1 gives me a 1. And I keep iterating this. 1 plus 2 is 3. 2 plus 1 is 3 again. 1 over here. And you can already see that the numbers that I had from squaring it, a squared plus 2ab plus b squared, or a cubed plus 3a squared b plus 3ab squared plus b cubed, right, are the coefficients that are showing up in front of those numbers, right? So if I keep doing this, right, and I'll write a few more rows down, then I could keep going if you wanted. This is the little hack that's going to tell me exactly what to do. So you want to figure out what a plus b to some number is. I just go to my triangle, and that tells me what the coefficients are, and I just write the expansion down, sort of decreasing the power of a 1 by 1, right? So for instance, if I wanted to do something like a plus b to the 5th, right? Very quickly, I just go over to my triangle over here, right? And it tells me, well, I'm going to get a to the 5th, right? Plus 5 a to the 4th times b, plus 10 times a cubed, b squared, plus 10 again, times a squared b cubed, plus 5 ab to the 4th, plus b to the 5th showing up. And here, I can then see from this, I ask you, does the freshman's dream hold on the 5 clock? In 5 clock arithmetic, any multiple of 5 doesn't matter, right? Or if 5 is the same as 0, right? So, well, 5, 10 is a multiple of 5, 5 again. So I see on the 5 clock, this works, but we can also see examples where it's going to fail immediately. So for instance, let's go one more row down, a plus b to the sixth. On the 6 clock, right, I can see that, well, 6 is fine, the other 6 is fine, but here 15 and 20 are not multiples of 6 anymore, right? So even in 6 o'clock arithmetic, the freshman's dream, a plus b to the sixth equals a to the sixth plus b to the sixth, does not hold.
Coefficients haven't come to our rescue and eliminated the letters.
That's right. So I can tell you what variant does hold. It's not very satisfying, maybe. So that's the freshman's dream on the 6 clock.
Not pretty.
It's just you get to forget 2 terms, but that's it, right? So not very satisfying.
So we can read off Pascal's triangle there quite easily in what mods it's going to work.
You can read, all right, so, and maybe you can already see it from what I've got, is you might guess, right? So, well, I see it works for 2, 3, 5. What do those numbers have in common? In particular, I also see it doesn't work for 4, right? And 6, right? So this is on the 6 clock over here, right? 1 plus 1 to the 6, right? On the 6 clock, right? 2 to the 6 is 64, which is the same thing as 4. Right? But of course, 1 to the 6 plus 1 to the 6 is 2, and so those two are not the same on the 6 clock.
Okay, but in general, you're telling me primes are the key here.
Primes are the key. So the claim is that if you look at Pascal's triangle, right? So, and maybe it's worth writing down sort of also the general case. I can. Do you want me to? So, right. So the general case here. So in general, the binomial expansion. The numbers that show up on Pascal's triangle are those, the numbers have the form n choose k. So the binomial expansion here says that a plus b to the n is going to give me the sums of these powers of a and b, where the sum of the exponents add up to n, and the coefficients you get here, n choose k, is the binomial coefficient n factorial over k factorial n minus k factorial. It's not clear if I write it this way that this really is an integer. I wrote a fraction on the page. Right? And it just so happens that everything cancels, and you can write this down nicely to see this, right? So that you actually end up with an integer, right? So, and these are the numbers on Pascal's triangle. In particular, you also have the relation that allows you to generate the whole triangle by adding things.
If the power is prime, that clock will give us the freshman's dream.
That's right.
The dream will come true.
Right? Or translated over here, the claim is that for any of the prime rows, I claim that all the numbers on the middle of Pascal's triangle, all of them are divisible by the prime p. And we can see that from the formula for the binomial expression, or whatever, these n choose k. Okay. Right? Okay. So in particular, right, so if I take p choose k, let me just for fun give this a name. So I'm going to call this number here capital N. Right? And here I want k to not be 0 or p. Well, from this expression, what do I know? I have that n is p factorial over k factorial p minus k factorial, or if I multiply to the other side, k factorial p minus k factorial times n is equal to p factorial. So I need one more thing to convince you that it's a multiple of p.
Yeah.
Right? I have to remember that the integers have the primes as their building blocks. So, so the integers, I can make any one of them by multiplying uniquely powers of products of primes. Right? So I have unique factorization. So, but if I look on the right side of this equation, there is at least one p. This is the product of all the integers p on down to 1. Right? So there is a p on the left side, which means that I have to end up with a p somewhere if I break this into primes on the left. Another way of saying it is p divides the right side, so it divides the left. And the thing about primes is when a prime divides a product of numbers, it divides one of those numbers. So p has to divide either k factorial, p minus k factorial, or n. But k is some number that is less than p, so it can't divide that. P minus k is some number that's also less than p. It can't divide that one, so the only thing left is that it has to divide n. It has to divide this binomial coefficient.
And that's why we know all the all right.
And that's why we know for all the primes this works. You can also see then that this doesn't work as soon as you have something that's not prime. You have to be more clever if you want to analyze which of the coefficients are divisible by n, or divisible by p, or divisible by whatever you like. And there are theorems like that. So there's a famous theorem called Lucas's theorem that talks about divisibility for binomial coefficients, what powers of primes they divide them, but that's maybe a subject for a different video.
All right, what's next?
The thing that's really behind the freshman's dream is that powers behave very differently in clock arithmetic than when you use regular arithmetic. And it seems a shame not to tell you another way, one of the very famous ways and very useful ways that powers behave differently in clock arithmetic, particularly for prime clocks. All right, so this is what's known as Fermat's little theorem. It's to distinguish it, of course, from Fermat's last theorem, right? So, which has a much longer and storied history than Fermat's little theorem, but maybe, at least in the real world, it's not clear which one is more useful to the common man. So, in fact, Fermat's little theorem is at the heart of a lot of encryption schemes. It has been used for RSA encryption and other things for a long time. So maybe here's the statement for you. If I take a prime, right, then the claim is, and maybe I'll use slightly more fancy notation here, right? So a to the p is congruent to or is equal to a mod p, or another way of saying it, right? So mod p here just means in p clock arithmetic. We can pick out many examples. Give me your favorite prime.
Oh, I mean, 7.
7 is acceptable,
Yeah.
right?
Okay.
Give me a number less than 7.
Okay, 4.
Right? Right? So the claim here is that, we have to know what 4 to the 7th is.
Oh, 4 to the power of 7.
4 to the power of 7, right? So,
Want a
but
calculator?
again, well, we could get one, but I'm going to cheat a little bit here. And again, the point here is that raising things to powers in clock arithmetic is just easy. Here, I'm going to look at, let's say p is 7, right? A is 4. All right, so I want to raise 4 to the 7th power, and I certainly don't remember what that is, but I can break it up, right, into something that I do remember. The first thing I'll do is, pull out 2 of those 4s, right? And now 4 squared is 16, right? But 16 on the 7 clock is 2, right? And I can repeat the same trick. So I pull out another 2, another 1, right? So 2 cubed times 4, and now we're in the money again, right? 2 cubed is 8, which is the same thing as 1 on the 7 clock. There I have Fermat's little theorem, right? 4 to the 7th on the 7 clock is the same thing as 4. So I just verified, right, that on the 7 clock. And it took me several steps here, but this also gives you an idea that playing around with powers on these clocks is much easier. I didn't have to write anything down here that was a double-digit number on the page, right? So it's very easy for me to raise things to really high powers.
This is pretty cool. It's pretty good fun. All this stuff you've showed me with clock arithmetic or modulo or whatever you want to call it. But of course, numbers don't do this. Like, numbers just keep going. They don't wrap back around on themselves and come back to 0. So it's like you've kind of made up this other kind of mathematics to make all these things work that shouldn't work. What's the point of this modular arithmetic? Is it like a useful thing? Like, is it a legit thing?
Sure, it's very useful. It's a little hard to say the number of places because it's just vast.
Clocks.
Right? So certainly clocks are one of them. Here I've played around with a lot of the clocks where they were very small clocks, right? But it's very hard for me to explain to you, we could be living in a world, right, ostensibly, where we were always working with one really huge clock, right? What's the biggest number you know?
Oh, like Graham's number, tree 3.
Yeah. These huge numbers, right? If I had a clock that was bigger than that, and you never saw a number bigger than that in your life, right? In reality, you might as well be working on a huge clock most of the time. And in fact, there's a lot of times computer systems to prevent themselves from going beyond and timing out on things. Computers don't like to deal with infinite processes. They like to terminate. So this gives you a way as a stopgap, right? Maybe that's not the most satisfying explanation, but it shows up a lot of places like that. A lot of the time, you also want to put yourself in a situation where you can do these tricks because the arithmetic is just so much more computable, right? So a lot of other computer systems will be based around these things. So you've probably heard of the binary numbers or things like that, right? So yes-no arithmetic, even odd arithmetic. This has a lot of real-world applications as well. So I have basically the slickest proof I know to convince someone that this really works. And again, it involves looking a little bit more at the properties that these kinds of clocks satisfy and what clock arithmetic really looks like.
Divisible by the number we're testing. It was 341. Thumbs up. Yeah, great. So it's passed the test. Let's try another one. Let's try another test. Let's do it with 3 then. We do this, 3 to the power 341 minus 3. Is this divisible? And this is where it fails the test.